Hi, my name is Avi.
Hi, my name is Sutton. This is Lab 7, Michelson Applications, and our TA is Lum. For the interferometer calibration in Part A, we started by aligning the Michelson interferometer with a Heaney laser and displaying the output on a white index card. We then adjusted the tip tilt of mirror 2 to create circular fringes. Circular fringes occur when mirror 1 and mirror 2 are parallel to one another. Once we saw the circular fringes, we moved the micrometer and counted 100 fringe cycles, where one fringe cycle is bright to dark and back to bright. We recorded both the starting position and ending position of the micrometer and used those values in our calculations.
The distance the micrometer moves is not the real distance the source is moving, so we found a calibration factor that would take the distance the micrometer moves and put it in terms of source movement. To do this, we rearranged the equation m lambda equals d to put it in terms of delta d and delta m. We used the distance the micrometer moved as d. Then we used 100 as delta m and the real wavelength of a Heaney laser as lambda. By dividing our experimental d by m lambda, we found a calibration factor of 2.592, which we used for the following sections of this lab.
In Part B, we measured the wavelengths of 3 light sources. We began by swapping out the Heaney laser for a laser diode and counted 100 fringe cycles on a white index card. For the sodium and mercury source, we looked directly into the output of the interferometer since the light wasn't bright enough to be displayed on an index card. We once again counted 100 fringes for each source. The starting and ending micrometer positions were recorded for each source and used in our calculations.
To find the wavelength of the sources, we use this equation. The distance between sources is the distance we measured on the micrometer, and the calibration factor puts it in terms of source movement. The m2 minus m1 is the number of fringes we passed. In our case, we counted to 100. We use this equation to find the wavelength of a laser diode, mercury source, and sodium source. The values we got are shown here. We had a 2% error for the laser diode, 6% for the mercury source, and 0.5% for the sodium source. This error likely came from miscounting the fringes.
In Part C of this lab, we measured the wavelength separation of a sodium doublet. To do this, we first had to identify the null points, which are points of minimum fringe visibility. Once we identified these points, we recorded the distance between them by moving the micrometer and recording both our starting positions and our ending positions. We used this data in our calculations.
Because the sodium doublet has 2 separate wavelengths, the wavelengths don't interfere, but their irradiances add, giving us the equation on the right. The first cosine term acts as a carrier, shown in blue, and the second acts as an envelope, shown in red. We measured the distance between the 0 points on the envelope, where the fringes disappeared. We found that the wavelengths were about 5.464 angstroms apart, when in reality they're more like 6 angstroms.